Okay, good morning, everybody. I'm going to go ahead and start a little bit early, just a few minutes. This is not required, but I'm going to go over the discussion sections that are on Canvas. And people have asked questions, and I want to see if I can just answer those right now in the few minutes before class. So here's the first question. What does it mean to be a molecular cloud that moves? That's a great question. I'm still confused by this. Who found this out, since they are hard to see? Well, it's a good question. I'm not sure who the original discoverer are, who that would be, but the principle that you need to know about that allows us to see the moving of the clouds, not clouds, is the Doppler effect. Okay, so the colors, the invisible colors of light are subtly changed by the motion of the clouds, right? Redshifted, oops, what did I just write? If they are moving away, and blue shifted if they are moving towards us. Okay, so that's actually how we know that they're moving, and that's true for any of the clouds. Okay, so let's see the next question. Protostars are not spherical. Anybody respond? Oh, yes, good. Knowing that there is a free fall phase for molecular cloud, which is the time it takes the cloud to collapse, and there is enough thermal pressure material there to determine how long it will take. Is there such a thing for protostars? Well, actually, you are forming the protostar. So absolutely, it's basically the same thing. Kelly, so the free fall, oh, I already said that. All right, never mind. Okay, the free fall phase, it is becoming a protostar. So the heating of the protostar leads to pressure, which slows down the free fall. So as the free fall is occurring, the mass is gathering from a great distance away. And as it's falling, it's heating. And eventually it creates enough of a pressure to slow that collapse. And that's no longer free fall. But what you have is this hot body that is basically your protostar. And it's continuing to compress the core till eventually it reaches that 10 million Kelvin and it begins the fusion process. And that will be the day it becomes a star. Okay, so you can read that a little bit more. How long does the process of protostar take to become a main sequence? Well, so this is actually, okay, great question. Okay, we have some good questions here. How long does the process take? And it turns out it takes different amounts of time depending on the mass. So let's see, Melody, okay. So Melody put a response. That's actually pretty good. Let's see. So let me go ahead and reply. So the greater the mass, the shorter the time needed to become a main sequence star. And actually, I should go look up some. There are examples, just a handful, by the way, of protostars in the process of forming. That we are watching, that scientists, the universal we are watching. I'm a scientist too, though. So, okay, so yeah, that's the answer. So let's see. Melody said, I want to respond to that. I have a partial answer. It has something to do with all stars living 90% of their life as a main sequence star. Yeah, most of their living life is going to be a main sequence star 90% of the time. And so say you're a scientist, you're observing star 1, you classify it as a blue supergiant. Then so actually, that is, we do actually the best way, okay, so I should just say, the best way we have for determining this time is simulation. Okay, and why? The time scales are huge compared to human lives, right? So the length of time we've been watching is very short compared to the length of time needed for a star for a cloud to collapse and form a protostar. It can take as little as like 100,000 years, maybe 100,000. I don't know, maybe it's only 10,000 years. I don't know. You know what? I'm not sure. It can take less time. It can take. Let me go the other way. As a billion years, maybe, right, to form the smallest star. I might be off on that, but I feel more comfortable with that than the other one. Okay, so that's a couple of questions, and I'll try to do that the next class as well. And yeah, that's a picture of a protostar, protoplanetary disk. And in the protoplanetary disk, you can see the rings, right? And each ring, there is matter that is coalescing to form a planet. Now, I showed you guys a video last time that was much more complicated, but anyways, yeah. So, oh, that's a great question. I want to answer that, but I'll answer that next time. Okay. So let's go ahead and go back to our class. Good morning, everybody. Good morning. And I am hoping that we have some people. Yay, there's Melody. Rise and shine. Yes, rise and shine. Welcome. I'm so glad. I was just talking about you, Melody. Thank you for your comment on the discussion section. And we are going to be covering some really cool stuff today. I put in there that you're going to blow your minds. If you don't already know about relativity, then trust me, you are going to be in for a really wonderful discovery. So relativity is, actually I can talk to you guys. Let me show you. I can say good morning. Good morning. Hello. Relativity is one of those amazing things. So I'm super excited that we have two classes to talk about relativity, because there are two different versions of relativity, and you have to know them both. So the one we're going to talk about today is called special relativity. If I happen to finish it, I'll move on and start talking about general relativity. So anyways, they're both awesome. One of them actually, neither one will do a lot of math. There's not any math, but I'll just talk about the math a little bit more. The other one, I'm just going to talk about the ideas. So, and you've already heard them because you watched the videos, right? And got 100% on the quiz, I hope. But anyways, we have two topics to cover, and I need to close this window and open up the window with our lecture slides. Sorry about that. And we are just going to finish. We only have a couple slides. I was so close to finishing, but I do need to finish. There's some good questions at the last part. We were talking about Jocelyn Bell, and I want to describe for you the final little thing there. And then we will begin chapter 14. Very exciting stuff. Okay, so let's see. Before I do that, let me go ahead and make sure that I've gone over everything on your website. So I'm going to click back here and click the student view so we can see what you guys see. Okay, and so let's take a look at our Canvas site real quickly and make sure that we know what's going on. So let's see. Oh, check this out. Extra credit. You can watch this movie and get 5 points of extra credit. It is a really beautiful movie. I love it. And then what you do is you take the quiz and you just answer these 4 questions. Okay. So give me a brief summary, like a 1-paragraph summary. Just tell me what the story's about. It's a really cool story. I actually think you could invite your roommates to join you, and they would probably like it too. I found it very inspirational. What did you find most interesting? What was one question you had? Because that's actually kind of the coolest part of learning, right? When you learn a little bit, you start to ask questions about what that might lead to. And I hope that as a science student, that's one of the ways that we are influencing you, right? Helping you understand that answering a question usually leads to 2 more. So anyways, and would you recommend it? Do you think it's a good movie? Should I ever show this to students again or never again? Throw it in the dungeon and never show it again, okay? So think about that and answer the question. And then I have some good news. I just twisted somebody's arm, and Jared Goldberg has agreed to do a Zoom video conference talk for us a week from Friday. And that will be another extra credit opportunity. And I would love it if you would come. I was actually hoping that this might be the biggest lecture that we've ever had, because we can have virtual people. We can have hundreds of people, much more than would ever fit in PS 101. And Jared has graciously agreed to talk about some of the work that he's doing, along with some really cool things that are happening in astronomy today. Okay, so you don't have any more crash courses. You can go back and review them. I think that would be a good idea. How about getting those 10 preview questions? Don't forget that the tutors have those questions. So click on the schedule and then click here and figure out who are you going to talk to today. You could talk to Leah, is how you say this. You could talk to Kenny. Jason is going to be available later in the day. So you've got 3 different people to talk to today. Tomorrow you have Kenny and Julian, and Thursday you have Tori and Jason again on Friday. Also, just keep in mind, besides just the tutors, we do have Liz, and Liz had some internet problems, so we lost her last Friday, but we are hoping, come on, move it, you got to move it. We also have Pal, and I will go ahead and send out a new link because we have to put a password on the Zoom now. So she will be doing Zoom on Wednesday and on Friday, 2:30 to 4. And hopefully you can join her. Okay. So let's see, new share. All right. So any questions? I'm gonna go back here. Anybody have questions? Say good morning to each other. Yay. All right, you're here. Good morning. I'm so happy to see you guys. And we have a very fun lecture in store for you. This is really mind-bending. I'm not kidding, right? I think you may even find it a little uncomfortable, but that's okay. Don't worry. I promise that at the end of it, what you're going to understand will hopefully, give you a little better sense of what the universe is like. The universe is not ordinary, and neither are you. There's nobody like you, and I'm so glad you're in my class. And hopefully you are taking care of yourself, which means more than just the physical part, the mental part as well. So we have to be really gentle with each other. Everybody is stressed and strained. So be gentle if you can, be kind, be compassionate, because you don't know what the other people are going through. So anyways, and hopefully you have somebody to talk to. If not the tutors, myself, you can send me an email. I haven't been doing my office hours. I really kind of miss that. Right now, I think the best thing to do would be to send me a request for a Zoom appointment, and we will have an office hour at actually when we are both available. Okay. So without further ado, if there are any questions, I'll look one more time. Any questions? No questions. Okay. So I will just get started then, because we have so much fun stuff here. Let's complete chapter 13. Here we go. Jocelyn Bell. So Jocelyn, we said before, was a radio astronomer, and she and her advisor, Anthony Hewish, built this beautiful telescope radio antenna array, and she discovered these pulses of radio signal. And at first she thought they were human made, right? They came from human beings. But then she did a study where she showed for sure that they didn't have, or rather that there was no parallax, right? So they were not local. And that means these are sources that are coming from space. And at first she, didn't really believe it, but she waited a little while and she found 2 more. So altogether there were 3 of them. They initially called them LGMs. It was kind of a joke, but you should know that, and you learned it last time, so I'm not going to repeat. Oh, I am going to repeat it. LGM stands for Little Green Men. They thought that they had finally heard from the aliens. And we really believe that one day this will happen, right? Just to understand, I am so convinced that there are other intelligent beings. There must be. I cannot believe that the universe would not allow other intelligent beings to exist. And therefore, it's just a matter of time. So one day, and hopefully we will be awake and aware and available to the aliens when they come to visit. And hopefully they'll be nice. Okay. Or else it'll be us going to visit them, right? Anyway, what was the Bade discovery? She found that there was a pulsar, but it turns out that there is a possibility when you have a large type 2 supernova, so greater than, actually greater than 20, wait a second. You only have to be greater than 8 solar masses to be a type 2 supernova, huh? But what if you had a really massive star? So the idea is that if you have a really massive star, that iron core at the end is going to be very massive. And I'll write it down in just a moment. But if you want to write it down, the mass of the core will be greater than about 3 solar masses. And so what do you get if you have more than 3 solar masses? So keep in mind, last time we talked about the strength of the neutron degeneracy pressure, and it was strong enough to hold up about 2.7 solar masses. That's my latest number, but not stronger. So what if you have 3 solar masses, right? This is an unambiguous question. I know the answer. There is only one thing. So what does the neutron degeneracy pressure do? If you have more than 2.7 solar masses, it cannot stop gravity. What do you get? And the answer is a black hole, right? So that is the end of chapter 13. So what I want to do is I want to make a quick table for you to make sure that everybody is very clear on what happens, right? So what happens? So we have different sized stars, right? So what I want to do is I want to put down the main, let me put this, main sequence. When it's a main sequence star, its mass on the main sequence, right? What does it end up as? How does it die, right? Type of death. Let's put type of death. Okay. And then what it becomes. And then what stops gravity. Okay. Oh, I should have said, oh, okay, I'll put what it becomes over here. Okay. So if you are less than 8 solar masses, okay, so remember that's the mass of the sun. So 8 times the mass of our sun, you will make, your hydrogen will make helium, your helium will make carbon and oxygen, but that's it. You won't have enough mass to use the carbon as a fuel. So what will happen is you will die a gentle death. You will collapse. Right? It's not going to be an explosion. You will collapse and you'll form a white dwarf. Okay, so in this part right here, I'll put the mass. Remember that the mass of a white dwarf is less than 1.4 solar masses, less than 1.4 solar masses. So this is my white dwarf. So what stops gravity inside of a white dwarf? Well, we learned this, right? It's the free electrons and the other electrons, the combination. It's the electrons, but actually what's the word? Electron degeneracy pressure. All right, so we're just kind of using this as a term. We have not studied quantum physics very much, but this is a quantum mechanical effect. I'm going to put that down, QM, quantum mechanics, right? It says that the electrons cannot exist in the exact same state, and so they repel each other to prevent that from occurring. Now, second state, right? If you are between 8 and about 20 solar masses, right? About 8 and 20, what happens to you? You are going to go all the way. You go all the way to iron, and you have a type 2 supernova. Okay, type 2 supernova. And so what happens then is what it becomes is actually a really interesting question. It turns out that this range, it may be that 20 is too high right now, but we said 20, and we think 20 is about right. So don't worry too much if it's not exactly right. But what you get is a neutron star. And so the iron that's left behind has too much mass for the electron degeneracy pressure to support it. So the electrons are forced into the nucleus where they find protons, and you get a big ball of neutrons. Okay, that's what you get. And so what is the mass? We think that it's about between 1.4 and about 2.7 solar masses. Okay, if you can't read that, try to listen to what I'm saying. So between 1.4 and 2.7 solar masses. I will scan these papers, by the way, and upload them to Canvas after the lecture. Okay, so now what stops gravity in a neutron star? And the answer is it's a big ball of neutrons. The neutrons themselves are going to stop it. And so we call it, just kind of learn the words, neutron degenerate matter. So it's called the neutron degeneracy pressure. And once again, this is a quantum mechanical effect. Actually, just a kind of little side, how big is a white dwarf, right? It's the size of a planet. Okay. Okay, so it's the size of the Earth, for example, 6,000 miles and 6,400 kilometers in radius, 4,000 miles in radius, 8,000 miles across, 12,800 kilometers across. That's how big a white dwarf is. The size, a planet-sized object with the mass of a star, right? How big is a neutron star? It's like 20 kilometers. It's the size of a city, right? A small city, in fact, not even a big city. It's 10 miles, 20 kilometers across, something like that. These are small, tiny little things. Okay, so my last category is greater than 20 solar masses. And what do you get? Well, of course, you get a type 2 supernova. So just a quick point. Do we know the mass of a type 2 supernova? And the answer is not at all, right? All we know is that it's bigger than 8. Anything bigger than 8, type 2 supernova. It goes all the way to iron and does a type 2 supernova. And what does it become? A black hole. So up until a couple of years ago, I would have said 3, but now all I know is that it's greater than 2.7 solar masses. And what stops gravity in this case? Nothing. There is nothing to stop gravity. Gravity wins and pulls the matter down into what we call a singularity. So we're going to talk more about this on Thursday. But anyways, this makes me a little bit ill, okay? And you may not understand yet why, but as a physicist, I am sickened by this concept, and yet I still have to teach you about it. So that's life. What are you gonna do? Okay. All right, so any questions? I'll go ahead and check for questions. If you have questions, go ahead and put them on the side. And if you don't, no problem. I hope you have some questions by the end. All right. So we are on to chapter 14. This is relativity. Okay, so everybody can see the slides because I went ahead. I'm just kidding. I'm joking. Sorry. I know I forgot to switch. I'm going to switch right now. Change to the screen, chapter 14. All right, here we go. Down the rabbit hole, relativity. So keep in mind that there are actually 2 different kinds of relativity. And the first one we're going to talk about today is actually called special. So this author is a little screwy in this chapter. So I will be going out and finding other things to share with you. And actually, if we were in the classroom, I really would have done a lot of this on the board because I like talking about it. It's really fun. But before we do, the special relativity, we want to show you something exciting. This is really exciting. In very recent news, 2015 was the very first one, we were able to see two black holes merging. And this is a simulation showing what happens. When two black holes merge, they actually are orbiting as companions, and they orbit faster and faster and faster until they finally merge. And they make this really exciting thing that Einstein could only theorize about, and they are known as gravitational waves. So I will definitely talk about that in a little bit, but not at first. But I do want you to be aware, this is a super exciting thing that is happening now. We actually feel the gravitational waves coming from space. And up until 2015, if I asked you the question, how do we learn about what is out there in the universe? The answer was almost entirely, we look at the light. That's it, we look at the light, right? We have telescopes, we look at the light. We analyze the light, right? But we now have a new way to do astronomy, and it's really significant, but it's too soon to see how important this is. It's not really in any of your textbooks yet, but very, very soon we will start to see results, more and more results. We already have some from gravitational wave observatories, right? LIGO is the first one and is currently the best way that we have of observing these gravitational waves, but there are plans to make bigger and more sensitive gravitational wave observatories. This is going to get much bigger than the visual or any kind of light observatories. So, and yeah, anyways, it's pretty exciting. So what is a black hole? A black hole is going to be the final win. Yeah, this is funny. Gravity's final victory. When does gravity win? Gravity always wins. It's just never stops, right? And so what stops gravity? And the answer is nothing. And it collapses down to something with a tiny size. In fact, what we call a zero radius singularity. And the density is supposed to be infinity. Gag me. Oh, gross. Okay, seriously, this sentence makes me feel ill. There must be something wrong. Okay, this is not right. This is not right. My beautiful universe would not do this to me. Okay, so, but right at this moment, that's the best we have. So I do want to let you know that there's hope that this is incorrect, right? That there's just some slight problems, and I will tell you about that because I want you to understand that we have so much to learn still, right? All right, anyways. So what is going on? Which of the following is true? So you haven't really heard much about this. And so this is just kind of like, actually more like a preview question, but guess what? It will be one of the questions you have to answer when you take your quiz. Which of the following is true? Gravity is not a curvature of space-time. Well, okay. Space-time is the same for different observers. Okay. Time runs slower near a black hole, and a black hole is visible in space. Okay, so think about that for a moment. Only one of these statements is true. And what could it be? So think about that. You can chat in the YouTube chat window if you want. Pretend that you're talking to your neighbor there if you like. You don't have to do that, of course. I'm just offering it as an option. It's more fun. Try to have fun, okay? Watching a lecture on YouTube is not fun. I get that. Gosh, I'm not very funny on YouTube. I should work on that. I'm going to work on my YouTube jokes. Okay. All right. Anyways, but then again, it's recorded, so I better not be crude or obnoxious. Okay. Anyway, which is following is true. Okay. And the answer is the only one that's correct. All the other three are definitely wrong. Is time runs slower near a black hole. And what the heck does that even mean, right? So we'll talk more about that. That's coming up actually on Thursday, not today. Okay. So what is our goal today? We're going to learn about special relativity. Actually, I think he put the words in the order that I disagree with. This is the theory of special relativity. Maybe I'm wrong, but actually, no, I'm not. He's wrong. Okay, it's the theory of special relativity. Rearrange the words a little bit. Okay, so we have a couple of learning goals. Electromagnetic waves, the speed of light, frames of reference, important ideas, relativity and space-time, and the twin paradox. We will cover that today. I did put a link, by the way, if after the lecture you want to watch Physics Girl, she has a 5-minute video. It's pretty good. She only made one major mistake. Actually, it's not even a major mistake. It's a tiny little mistake. Actually, sorry, it wasn't major at all. It's tiny. But she made one little mistake, and I'll go ahead and tell you about that. It's a very small mistake. Okay. All right. So here he is, Mr. Albert Einstein. And one of the things that we want to talk about is how did he come up with this theory of relativity? What did he do? How did he figure this out? And I have to be honest, it's pretty amazing. I mean, it's just amazing. And how did he figure that out? He did have some clues, and he was not by himself. We're leaving out some other names. There were some people that worked with him. He was not alone, right? But anyways, he's given most of the credit, and he did do some amazing things. Okay. So a few years before Einstein grew up, actually around the time of his birth, this man by the name of James Clerk Maxwell was studying electricity and magnetism, and he discovered something amazing, that he could take these equations, which had been separate equations, and just for fun, it was almost just a lark, like, let me see if I can do this. He put them in a mathematical equation that we call the wave equation. And why did he do that? And what was well, I was just kind of curious. Is it possible to make a wave with electric and magnetic fields? And the most amazing thing happened. If he found out that yes, it was possible, and the coolest thing ever, it was a self-propagating wave. And that was a weird idea, but he's like, wow, this is weird. And then, quite by accident, when he did the calculation, how fast would this wave go, he discovered that it was the same speed as light. He had just discovered that light is an electromagnetic wave. Wow, it was such a cool, happy accident. And Einstein, would have read that, work and been influenced by that, of course, as a young physicist. But yeah, there's some interesting things there. Okay, so before we jump into light and before we jump into relativity, let's talk about ordinary situations, okay? So I have this is actually a little strange for us, but if you were ever to go to Mississippi or to the Mississippi River, this is a big river. We don't have any big rivers around us. We have the ocean. You could think of it like the ocean tides or something, or the currents along the ocean. But the idea is that there's a river, and the river is flowing in this direction with a speed of 7 kilometers per hour. So here's this fellow who's watching the river, and from his point of view, he sees the river water going in this direction. Now, the people on the boat don't see the river water moving in that direction because they're moving along the river at a speed of 12 kilometers per hour. So they see the water moving backwards 12 kilometers per hour. If we stepped off the boat and into the shoes of the person on the riverbank and said, how fast do you see the riverboat moving? The answer is 5 kilometers per hour. And the reason is that the water is moving and the boat is trying to move on top of that water. And these two velocities are not in the same direction. And so they end up subtracting. And so actually it's just, oh my gosh, I did this video. Oh my God, I wonder where it is. I don't know where it is. Hold on. I'm just feeling a little gratuitous. I don't know. Have anybody heard of a people mover? This is cute. Relative. I know some. I did one, and I don't know where it is. I just recorded it one time. But let's see. I'm going to go ahead and show you a YouTube video. I hope it's good. I've never seen it before. That's risky. This is a risky click. Okay, but I'm going to go ahead and show you. This is, I think this person is going to do a good job. Relative motion. Okay, so should we listen? Okay, so there's people on, I've done the same video. Oh my gosh, that's great. Should we listen to them or no? Anybody want to listen? Okay, let's listen. Let's hear what he says. You hop on the people mover. And so this is his daughter, because I've done the same experiment with my son. So Natalie is not moving relative to the people mover. So she is just moving along with the people mover. Now, if she walks in the same direction as the conveyor is moving, she gets a boost to her speed. You add the velocity, and look at her. She is going in the opposite direction. She is walking relative to the conveyor at exactly the same speed that the conveyor is moving forward. So from our point of view, she is not moving. Oh, I like this teacher. That's a great video. Okay, so does everybody get that? Okay, so it's very silly, I know, but it's just wonderful. Us science teachers, we know how to have fun. Oh my gosh, I should see if anybody has comments. Anybody have comments? Okay, yes. Okay, we found a good video. That was a great video. That was perfect. Okay, so back to our slides. And so actually relative velocity is the concept that relative to us, how fast does an object appear to move? And so everybody's got different perspectives, right? So I have a perspective standing on the side of the river, but what if somebody was in the river and just floating along with it? They would have their point of view, their perspective, and then somebody on the boat has a perspective. Each one of these is called a frame of reference. A frame of reference. This is kind of an important concept. A frame of reference is the place where you are watching the world. And reality depends on where you watch the world, right? What happens when you do an experiment? Well, where are you watching the world? So it turns out that this is a pretty, actually, you know what? It turns out that I need to talk. I feel the need to talk. I feel the need to describe something to you. So Einstein, was well versed with these ideas, and he actually, was thinking about it, I guess, and he came up. We think, ooh, that's a feather. He came up with an idea, an experiment that he did in his head, and only in his head. But he asked this question, and this is a very famous question, so I want to tell it to you, and you can try to answer it yourself. Okay, but Einstein answered the question and changed the world forever. So anyways, it's an interesting question. Here's the question. I'm sitting in a room and I'm looking at my reflection, right? So actually I would usually draw a picture. So let me just do what I normally do. Okay, so here we are. We're just trying to be normal here. We're going to go to my camera here, and I'm going to draw a picture for you. So we're sitting in a room, right? We're sitting in a room, and there's a mirror, right? There's a mirror. I'm looking in the mirror. I have lovely Einstein hair, right? All right, his lovely hair, and he's looking at his reflection, and he's smiling because he's a good-looking fellow. So there's a light here, right? There's a light that's shining in every direction, right? And how does it work? Well, some of the light bounces off of my face, or in the face of Einstein. It hits the mirror and then bounces or reflects and goes back to my eye, right? So this is actually what's going on when you see yourself. You see reflection. The light photons are reflecting off of your face. They're reflecting in the mirror and then back to your eye. It's a pretty cool little thing, right? That's what's going on when you see your reflection. So, Einstein's trying to think of a good question, and he says, but what if the room were moving? What if the room was moving forward at c, right? Remember what c is? The speed of light. So here is the famous question that Einstein asked. Would I see my reflection. Okay, so that doesn't seem like a big question, but it turns out it kind of is. And he had to decide one way or the other. So I want you to stop. I'm going to pause the video for a moment or whatever, just pause for a moment. I want to ask this question. I want you to decide one way or the other, because Einstein had to decide one way or the other, and he picked something that we were going to go ahead and agree with. But I wonder what you would pick. Would I see my reflection in this room that's moving at the speed of light? Okay, so what did you pick? Well, I'll tell you what Einstein said. Yes. He said, you will not know you are moving. Right? You can't feel your speed, so it feels normal. Okay? When you are moving at a constant velocity, you can't feel anything happening, right? There's no sensation of speed. So the very, very, common question to ask you would be to see, have you been on a plane and had the experience that you don't feel like you're moving, right? Can you be on a plane and feel as though you're not moving, right? And as long as the air is still, the answer is yes, right? If you're on a plane, you can actually do little experiments. You can drop things and they fall straight down, right? Yeah, you don't have to be on a plane, by the way. If you are a passenger in a car, don't do this if you're the driver, and you did this experiment, right? As long as the car is moving at a constant velocity, then everything feels kind of normal. You can do little experiments, you can throw things in the air, they come back in your hand, and everything feels normal. You can't feel your speed. The only thing you feel is acceleration. So when you're speeding up, when you're slowing down, when there's a bump in the road or there's a bump or turbulence in the air, that's what you feel, right? So you don't feel speed, you do feel acceleration, right? We have no sensation of speed, only acceleration. And so Einstein decided that this was it, right? That you and I would not be able to tell that that we were moving. Now, up until a few years before, actually, even as Einstein was working, there were two researchers that were trying to discover if light needed a medium to travel through the vacuum of space. And these two researchers are called Michelson and Morley, right? And they did a pretty famous experiment. So I'm going to share that with you right now. This is called the Michelson Morley experiment. And what they did is they put an apparatus, they had an apparatus on a very heavy weight, right? A stone slab. It's called an optical table. And they did this experiment and where they shine light, and the light is then divided into two paths. I think we're going to have a picture down here. Well, before we do that, okay, here's the idea. The idea is that suppose there is this stuff called ether, right? And it's invisible, we can't see it. But maybe this is the stuff that makes light able to travel through space, right? Maybe instead of empty space, there is this stuff called ether. Luminous ether means the material that allows light to travel through space. See, people were still uncomfortable with the concept that it could be self-propagating. They thought that like sound waves and like water waves, like earthquake waves, you needed a medium, right? Something to carry the disturbance. Waves are disturbances, right? So how does light travel? Okay, so there's this ether that I can't see, right? Well, if you can't see it, that's not really science, is it? So this experiment was designed to see the effect of the ether. And the concept is that the sun is flying through and the ether may have some flow, just like a river. And because the earth goes around the sun, at different times, the earth will be moving with the ether or against the ether, right? There must be times when it's moving with or against. And what does that mean? Well, if the ether is what the light is traveling through, then we should see light travel at different speeds. Okay, that's an important concept. So they did the experiment and they divided the light up into two paths, and one path went this way and another path is 90 degrees to it. So one of these paths should be affected, one of these paths. In one of these directions, you know, we're either going with the ether or against it. Not in both of them, though. It's not possible, right? It can't be possible that it's in both of them. So what would happen then is the light would be affected in one path, but not in the other. And what would happen is the light would take a little bit longer to travel this path than in this path, for example. And when they come back together, the light waves are going to be put together in something called an interferometer. And so, you know, we don't study this too much in our class, but the idea is that light waves can interfere, right? And so what that means is, I think we'll have a picture, is that the waves have high points and low points. And if two of the waves are together, if they're both at high points, which would happen if they take the same amount of time, then what will happen is that the waves will add together and make a bigger wave. This is called constructive interference. But if the waves are doing the, I don't see if there's a picture. There's no picture. Oh, well. Okay, too bad. Just take this picture and shift it a little bit. Take this wave. So if one wave is slower than the other, then shift this back a little bit. So this piece is right above this piece here. And what happens when the one wave is slower is it can, when it gets to the final location where they combine, it's not doing the same thing as the other wave. And then a low point and a high point combine, and what we call destructive interference. So this is something that we can see in the laboratory. In fact, this is an example right here. We see these bright areas and these dark areas. This is a fringe pattern, an interference pattern, and all waves do this. So a bright fringe right here is a constructive interference. The light is stronger. A dark fringe is where the light canceled out. So if you see this effect, you know that one of your waves had to go through, which was slowed down. Okay. So anyways, blah, 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 blah. Actually, I guess that's about it. This is the laser version. It's kind of strong. And so what they did is they did this experiment looking for a change in the light, and they did it for like 20 years. And every day for 20 years, they tried it. And guess what happened? Nothing. Okay. So there was no effect. Therefore, they concluded after 20 plus years of finding no effect, there is no ether. Okay. So Einstein would have known that. And so when I tell you that what Einstein tells us, he did use these results. These were an important part of what we're about to discover. Okay, are you ready? Because I need to begin by telling you Einstein's two postulates for special relativity. Okay, so you need to know them by heart. You need to memorize them. Okay. So what are these postulates? These are the assumptions. These are the two things that he's going to say. This is true and this is true. And from this, the two postulates of special relativity. It's too big a word for me to write the whole thing. That's special relativity. Okay. Number one. Okay. The laws of physics, you should write these down. The laws of physics are the same for all inertial reference frames. Okay, so this is a new word, or actually it's not a new word. We've used this before, inertia, right? We talked about Newton's laws of inertia. But the laws of physics are the same for all inertial reference frames. What does this mean? If you are moving, or you're not moving, let's say you're not moving, but there's a car that's moving, right? Let me draw a little car here. Old-timey car with the fins and everything, cool. Like when I was a kid, I had a car like that. 63 Pontiac Le Mans. Yes, that's right. I drove a 63 Pontiac Le Mans with a giant, it was a tank. I didn't tell you how I destroyed it. But anyway, it's moving with some velocity, right? This is very close to Einstein's drawing. There was a frame of reference that's not moving. This is the stationary, not moving. And this is a moving reference frame. We call it S prime, the moving reference frame. Okay. And I do an experiment. I drop something, right? It falls. And if I drop something here, it falls, right? Gravity works the same in both of these reference frames. But in fact, your reflection can be seen as well. If I'm standing still or I'm in a room, I can see my reflection. The laws of physics are the same for all inertial reference frames. So what does that mean? Moving at a constant velocity relative to another frame. Okay, so don't make it too hard, but if you have any questions, please ask the questions on the side. So if these two frames of reference are moving at a constant velocity relative to each other, they are called inertial reference frames. And the laws of physics are the same. Now, something wacky does happen if you are in a car and you are accelerating. You might have felt it, right? You feel pushed back into your seat, right? You feel pushed back into your seat. It's actually not happening, right? That's not what's going on. But how many people know what I'm talking about? You feel pushed back into your seat. You can't explain why, right? You're pushed back into your seat, but you don't understand what's going on. You don't know the reason why. And the reason is, it's not that you're being pushed, is the seat is pushing on you so that you can keep up with the car, right? So from the observer out here sees, right? I can see, if I'm watched from outside the car, I see the seat pushing on you to cause you to accelerate. Presumably accelerate with the car. So if the seat didn't do that, you would fall out the back of the car, huh? That's a bad car. Anyway, so the feeling that you get, you can't explain it. I can explain it if I watch you, but you cannot explain it. There is a fictitious force. This is called a fictitious force. So it doesn't have a law of physics that can explain it, right? There's no law of physics to explain why I'm feeling it. And the reason is I'm an accelerating reference frame. So these ones are not, right? You can't use special relativity in this case, right? It doesn't work. There are fictitious forces that I can't explain. Okay, so number one, the laws of physics are the same for all inertial reference frames. I don't have a lot of room, so I'm going to skip to the second page. Postulate number two. This is a big one. This is a huge one, but I have to trust you that you're gonna say, okay, this is weird, but this is true. Sean tells us this is true. Einstein was the one who first told us that it's true. Here's what it is. The speed of light is the same for all inertial observers. Actually for all observers. So I don't need any of that. Observers. Anyone who sees the speed, sees light, if they measure the speed of light, they get the same number, right? C. It's always C. Okay, now this one is the hard one. This is the one that you have to, this is the one that's going to screw everything up. And when I say screwed up, I mean actually just be real. This is the reality. And we just have misunderstood reality for such a long time. And the reason is most humans will not move anywhere near the speed of light. Actually, I've never heard of a human going that fast. Parts of a human maybe, but not any whole parts. Okay, so you can't go that fast. It's too fast, right? Human speeds are tiny. They're really, really small. Okay, so as a result of this, this is a human speed, right? Human speed. The human speeds are really, really small. Okay, so most of us have never had to worry about the effects of special relativity, but we need this now, right? We need it. It's part of our lives now. Okay, so let's go to the slides again. Okay, so there is no ether, right? There's no ether. Light is different than the rest of the world, right? It's something a little bit different. Okay, so we said these already. These are the postulates. Number one, the laws of physics are the same for all observers that are in uniform motion. They're inertial reference frames. And number two, the speed of light in a vacuum is the same. Okay, those are the two postulates. So this is a little strange though. This is actually, he wants to make sure, the author wants to make sure you get it, right? This is a little strange. Here's a story, right? There's a train and it's moving 45 meters per second in this direction. Somebody on the train throws a bag of, this is US mail, how about that? At a speed of 2 meters per second. Now this person says, no problem, I can catch that. It's only 2 meters per second. But what if you were outside the car and there was a big window here and you could watch it? What would you see, right? You would see if somebody throws this at just 2 meters per second, how fast do you see it coming to you? And the answer is not 2 meters per second, right? Because if they hold on to it, how fast is it moving? It's moving 45 meters per second already. So if they give it a boost of 2, you see 47 meters per second. Anyways, the speed of light, I don't know why you wrote it like this. Just ignore that. Okay. So, okay, so blah, blah, blah. Actually, the only thing that's good here is this word. Can you write down space, time? Einstein came up with this concept that space and time are connected to each other, that we live in 4 dimensions. And the 4 dimensions are length and width and height and time, right? These are 4 dimensions. And he saw that actually he's gonna teach us something really amazing about space-time. But before we get to that, we want to try to come to an understanding of what happens when things move very fast. So relativistic velocities require you to be moving at least 10% the speed of light. This is the way we write 10% the speed of light. So I'm going to actually leave my share for a moment because you need to be able to see this and say, what does that mean, right? So we just said 10% of c. How do you write that? And you write 0.1. It's just a decimal version of 10%. c, right? We use the speed of light to describe the speed, right? This is our speed v. This is our speed v, right? So what if it was 50% of c? What would we write? I'm hoping you guys understand. You'd write 0.5 c, right? Half of c. But if it was 70%, right? This is easy, right? 0.7 c. How about 99% of c, right? Okay, 0.99 c. Now, human beings don't go that fast, right? Human beings never go very fast. But we can shoot electrons, right? What is the fastest? I'm going to write this down for you just so you know. Fastest speed electrons that we've ever accelerated. How fast have we made electrons move? Okay, and this is going to be kind of crazy. Ready? The fastest speed electrons actually moved 0.99999. That's 5. 99999. That's 10. 8, 8c. So as you can see, they've gotten incredibly close to the speed of light, right? If I had to write this down, I would write 99.999999988% of c. It's not the speed of light, but it's incredibly close, just so you understand that, right? So human things, no. Electrons, yeah, we can go really fast, okay? All right, so back to our story. Okay, so Einstein is going to tell us all you need is love, right? There, I did a joke. All you need is love. I'm going to write it on my paper. All you need is love. La, 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 love. All you need is love. So what is love? Love is special relativity. I'm being goofy. Thank you. All right, all you need is love or special relativity. Same thing, okay? I'm just kidding. Okay, you don't need special relativity to have love. Okay, I love you. All right, here we go. Talking about relativity. Einstein actually would say to you that if you were on a rocket, let's make a rocket. Put a rocket, and I want to talk a little bit about the speed of light thing. You're on a rocket, and let's say that your rocket is moving 0.5 c, right? And you know what that means now, 50% the speed of light. And suppose that I shoot a laser beam, to communicate with my friend. I shoot a laser beam at the speed of light, of course, right? That's the laser beam shooting at the speed of light. If my friend is back on Earth, right? Here's Earth, and he looks at the light, right? He sees this laser. This is the laser, right? The laser comes to him, right? How fast does he see this moving? And the answer is he sees it move at c, not 1.5 c, right? You don't add these two together. He just sees c, no matter what. Okay, this is weird, but let it go. It's just the way life is. Okay, this is reality. Reality. Back to life. Back to reality. Okay, so this is the idea. The second one, the speed of light will always appear to be c. So whether you shoot it from a rocket, c, or the person who sees the laser sees c as well. Okay, so there's no relative speed for light. There's no relative speed for light. This is weird, right? This is weird, right? But that's the case, right? There's no relative speed for light. Okay, if you are ready, I'm ready to begin with the most important part of special relativity. And that is the concept of time. I'm going to give you a little hint. It's called time dilation. Okay, you need to know time dilation, but you also need to know what is it? Why do you experience it? Okay. So we're going to go ahead and describe, and I would have done this on the board with you anyways, right? We're going to describe an experiment. Okay, so I'm in a room and I want to do an experiment. I'm going to use light because light is an important part of what we want to do. And actually, I'm going to go ahead and make a light source, a laser, that shoots straight up to the ceiling, right? There's a laser, okay? And I'm inside this room doing this experiment. And the room has a certain height, right? I'll tell you why in just a moment. And what I'm going to do is I'm going to press a button. The laser is going to fire up at the roof. And it's going to hit a mirror right here. And it's going to bounce back down. And it's going to hit a detector on the floor. That's supposed to be vertical. Wow, that doesn't look vertical. Just pretend it's vertical. Sorry. There you go. Okay, and I'm going to measure the time. Now, the time, that really doesn't look good. Oh my God, that's such a fail. Let me, you know what? I was looking at the camera while I was drawing. Try it again. Actually, this at least should look a little bit better than that. Okay, so I'm on this car. Okay, the light goes vertically up and vertically back down. Okay, so the laser goes up, the laser goes down. Okay, there's a height h for the room, and I'm going to measure the time, right? So the time that's measured where the experiment is taking place is called the proper time. You want to write that down, right? Proper time. The time measured where the experiment is taking place. Okay, it's called the proper time. Proper time. Okay. So we're going to give it a symbol, and I have to use a symbol, so I'm going to call it T0. Okay, so T0, that's the proper time. And if I were doing more math in your class, I could actually write down a formula for you. It's actually pretty simple. If you want to know the distance, the time something takes, you take the distance traveled divided by the speed that it's traveling. It's a pretty simple formula. You can, you're going to go travel to LA. 100 miles away at 50 miles an hour, it takes you 2 hours, okay? So this is a pretty simple calculation. But in this case, the light is going to move up a distance h and then back down a distance h. It's going to go 2h. And how fast is it moving? Well, it's moving at the speed of light. So this is the time that I would measure. I know that this is what I would measure, okay? I don't even have to do the experiment. I know that when I do the experiment, that's what I'm going to get. So that is the reality for me. The light moves vertically up and vertically down. So that is my reality, and I'm sticking with it, right? So you should always pick, by the way, my neck is super long. Isn't that funny? Okay. So you should stick to the version of reality that you see. But here's the question. Does everyone see the same thing? And the answer is no, because what Einstein did is he imagined that this was actually a car on a train. And in fact, this experiment, so this is the experiment, this is seen, this is from the frame of reference, the reference frame of the car, right? The car or the train car, right? The rocket, it'll be a rocket in a few minutes. But there's another person who's watching the car go by. And this train car go by, and they see it moving with a velocity. And this is now going to be the story, the reference frame of a person on the side of the tracks, right? So in other words, there's a moving reference frame where I'm doing the experiment. And then there's this person who's standing watching the train go by on the train tracks, right? And they see the train moving with a velocity v. And their reality is different than the reality of the person on the train. And I want to explain what I mean by that. This is an important concept. You will not see the same thing. So imagine that there's a window and the side of the car, you can see right through the side of the car, okay? I want you to imagine that the laser is released from this point right here. The laser is released, right? Sorry, I just had a little technical glitch. My computer was, my battery was going down. I'm like, I have it plugged in, but I didn't. Actually, it was not plugged in. Oops. Okay. So the laser is released, and even though light is super fast, it takes a little time to get up to the ceiling. The car is moving. Will the mirror be there anymore? And the answer is you must remember that because the car is moving, the mirror has to move with the car. So I want you to imagine that by the time the car gets to, by the time the light gets to the ceiling, the mirror is actually over here. So now the question is, did I see the light reflecting off the mirror? Well, yes, I did. So then the question is, from my point of view here, could the light have moved vertically? And the answer is, if it moved vertically, it never hits the mirror because the mirror won't be there when it gets there. In order to hit this mirror over here, the light is going to move along a diagonal path, right? So I don't see the light moving in a vertical path. I see the light move on a diagonal path. And this diagonal path is based on how fast the car is moving. By the way, if the car stops moving, it becomes vertical, right? But the faster the car goes, the more the car will move forward, right? The bigger, the more diagonal it becomes, right? So this thing, the faster the car goes, the more it leans over like this, right? If it's not moving, it is vertical. But the faster the car goes, the more it has to lean over. So that's what I see. That's what I see. That's my reality, right? This is my reality. Which one is real? They're both real, right? They are two different reference frames. You don't see the same thing. So the light hits the mirror and then bounces, right? And then comes back to the detector on the floor. But again, it can't be that it bounces straight back down, because by the time it gets back down to the floor, the car has moved over here and the detector is over here. So what happens? The light has to bounce again on a diagonal path. Sorry about that. It's a little crooked. All right. So now the question, if we don't see the same thing, that's fine, right? We just don't see the same thing. One, the light goes up. This one, the light goes along a diagonal. No problem, right? Is everybody okay with that? Now I'm going to actually just go see. Is everybody okay with that? Do you agree? Is that okay? You just have different frames of reference. Different frames of reference. It's not a problem, right? It's what you see. Is everybody okay with that? I'm actually hoping everybody's fine. It is moving. We don't feel it. Yes. Okay, good. That's a good point. So everybody's okay with this. Okay, good. Because I'm about to tell you something important. If I were to measure the time as seen by this observer, right, by this person, is it the same amount of time as this person sees here? And the answer is no. It's t. And why is that? Well, because the speed of light is the same for all observers. So if the light moves vertically up and down, and by the way, the height right here is still the height of the car, that hasn't changed. But the light travels along a longer or shorter path now. And the answer is it's a longer path. And therefore, if the distance is bigger, the time must be longer. So the person here literally sees more time passing. This time machine is greater. Let me put that, is greater. Okay, so here's the funny thing. I'm going to go ahead and show you an equation. This is the time dilation equation. You don't actually have to really use it much, so don't worry. But I am going to show you a tiny little bit of math because I'm your teacher, and that's what I think is good for you. I'm just kidding. But anyways, I want to show you because I love it because it's so fun. Okay, so I'm going to write down the equation. There is a factor by which time is being dilated. And so I want you to write this factor down. It's known as gamma. Gamma. The name of it, if you want to look it up, it's called the Lorentz factor. Times the proper time. So the way that dilation works, remember what happens when your pupils get dilated, right? You have a small pupil, and then you have a dilation, right? In the dark, what happens to your pupils? They get larger, right? Dilated pupils. What happens, right? Your pupils got bigger. That's dilation. Well, so that's what happens to the person who's watching. They see each moment that is lived by the person on the train car to be stretched out, and therefore takes longer for them. So the crazy thing is that clocks do not tick at the same rate. Okay, this is kind of crazy. This is our first effect called time dilation. Okay, so what is this factor gamma? What the heck is going on? And again, this is not a mathematical class. Okay, so I will not ask you to do this exactly on a test, but I just want to show it to you so you have some idea. Otherwise, I'm going to tell you about something and you'll not understand why. Why does that work? That's 1 divided by the square root of 1 minus v squared divided by c squared. So v is the speed of the car or the rocket or whatever. Okay. So let's just do some examples, and then you'll understand how easy this is. It's actually really not very hard, but anyway, let's start off with like, I don't know, 0.5 c, right? Half the speed of light. So here's how you use your gamma, right? So you go gamma 1 divided by the square root of 1 minus 0.5 c squared divided by c squared. Now you'll see why we do this, right? When you square parentheses, what do you square? You got to square both of the things, right? So I'm going to put an equals 1, okay? And I'm going to do this, 1 minus 0.5 squared times 0.5 squared is 0.25, right? And then c times c is c squared divided by c squared. What happens when you have c squared over c squared? They cancel. And so the trick is that this is actually a really easy calculation to do. We just get 1 over the square root of 1 minus 0.5 squared, right? Just so I can show you, right? It's this 0.5 here becomes a 0.5 squared inside of the parentheses here. Okay, so what is 1 minus 0.25? That is 1 over the square root of 0.75. Okay, so I get out my handy dandy calculator and I try this out, right? And again, I'm not going to be doing this with you. If I tell you anything about gamma, I'll actually tell you the value of gamma, right? I will make it super easy. So 0.75, take the square root of that and 1 over that number, and I get a gamma of 1.15. Okay, so it's just a little bit bigger than 1, a little bigger than 1. Okay, just a little bit bigger. And so it's not a big effect right now. This is not a big effect, it turns out. It's 15% effect. That's the 15% effect. Now, I should have mentioned something kind of important. Einstein understood that if relativity is real, then when you go into a situation that's not relativistic, it should go back to kind of normal physics, right? The normal thing. So just for, I forgot to show you something. What if V is 0, right? What if V is 0? Well, gamma equals 1 over the square root of 1 minus 0 squared over c squared. Well, that's just 0, ignore it. So what do you get? Gamma is 1. So if the speed is 0, you go back to 1, which means that if you look at this equation, 1 times t0, they will measure the same time, right? There's no difference in the time now, right? The times are the same. And the reason is they're in the same, same frame of reference. Sorry about that. So if you were in the same frame of reference, you measure the same amount of time. Okay, so if you're in the same frame of reference, you measure the same amount of time. Okay, let's do just a couple more, 2 more, okay? So let me do V equals 0.9 C. Okay, I'm gonna do the quick trick. You can try to do this at home. You get 1 minus 0.9 squared. Well, 0.9 times 0.9 is 0.81. So I get 1 over the square root of 0.19. And that's a bigger number, right? Okay, 0.19 square root, 1 over that number. And I get 2.29. What happens to gamma when you go faster? Okay, it gets bigger. Okay, let me do one more, 0.999 C, okay, which is not even the fastest, but I just want to try it. 1 over the square root of 1 minus 0.999 squared. And I'm just going to do it in my calculator this time. 0.999 squared. Take that away from 1, take the square root, take 1 over that number, and I get 22.4. Okay. All right. So you could try this at home, but the basic idea, what happens? The faster you go, faster V is, the larger gamma becomes. Okay. Okay, one last one. What happens if you go the speed of light? Okay, well, we actually have a problem, right? 1 minus c squared over c squared. What's that? 1 minus 1 is 0. 1 over 0 is infinity. Okay, we have a problem. This is not possible. Infinity is not possible. We can't have that. So we're going to learn that you can't go the speed of light, but I wanted to show you that so you can see how it works. Okay, so I actually have an illustration, an animation of this that I want to show you. Actually, 2 things I want to show you. This is actually really cool. A buddy of mine, Don Ion, in physics, created these simulations. And relativistic clocks. Okay. Let's see if you can see this. Hopefully, can you let me know if you can see this, by the way? I'm pretty sure you can. I think you can. Let me know if you can't see it. Actually, let me see if I can ask that question right now. So you guys should see a clock. Okay. This is the light pulse going up and back down again. Everybody see it? Now, 0.9 squared is 0.81. 1 minus 0.81 is 0.19. I did the math super fast. Sorry about that. Okay, nobody's telling me that they can see it or not. Okay, so hopefully you guys can see it. So now if we do this experiment on a moving train, right, then you can see that from the 2 points of view, you see 2 different realities. There's 2 different versions of reality. And which one is correct? Well, they're both correct. They're 2 different versions of reality. Time is relative to motion. It is not the same, right? And so this is a crazy idea. There is no such thing as absolute time. Okay, so there's the math. You don't have to do the math. Okay, so you don't have to do the math, but time is relative. Time is relative. So if you are watching a rocket moving very fast, right? And you ask the question, how old are the people on the rocket and how old am I? It turns out that, you know, you can get these really weird ideas. So let me go ahead and take a situation where it's called the twin paradox. The twin paradox, and I'll tell you about the paradox in just a moment. And I'm going to give you a gamma of 10, right? I'm going to give you a gamma of 10. Now, you don't have to worry about what the speed is, just I know that the gamma is 10. So what's going to happen? I'm going to actually, I'm going to do this. I'm going to leave the Earth in my rocket, and I'm going to go to the nearest star. What's the nearest star? You guys might know this, right? It's called Proxima Centauri. And it's about 4.2 light years away. So I should just tell you, by the way, that if you're moving at this speed to have a gamma of 10, you're moving at nearly the speed of light. On Earth, if I watch them take this trip, I'm going to see them moving almost at the speed of light. It's going to take them 4.2 years to get there and 4.2 years to come back, right? So there's going to be a twin who stays on Earth, and a twin who gets in the rocket ship. They are exactly the same age when they start. Okay, so the twin on Earth will age how old, how much, right? Well, she will watch the rocket go there and back. She will age 8.4 years, right? She'll be 8 years older because she watched her sister go there and back again. Okay, this is the time that she experiences, T. Okay, but the twin on the rocket is going to age less, right? She ages T0, which, by the way, here's the equation. T equals gamma times T0. How do you get T0? It's T divided by gamma, right? I just inverted the equation. And so she's going to see 8.4 years divided by 10, or 0.84 years. I just did the math, okay? So she's less than 1 year older, right? She's less than 1 year older, but her twin is 8. They're not the same age anymore. Okay, so that's not the twin paradox, by the way. The twin paradox is that if you are in the perspective of the twin, okay, and you say, and you watch what's going on, you don't see yourself moving. You're not moving. What you see is the Earth is moving backwards, right? And the star is moving towards you. And so you are the one that's standing still, and the Earth is the one that's moving. It's kind of like you are standing still, the Earth is moving. That means what? That your age, you should age more than your twin who's back on the Earth. That there is no way to tell who is moving if you just look at this situation right here. If a rocket is moving away from the Earth, or the Earth is moving away from the rocket, it looks identical. And therefore, you should be aging more than your twin on the ground. This is the paradox. There is no way to tell who is moving. Okay? So that's too bad, right? So actually everything I told you is wrong, right? Well, actually it isn't. The paradox is resolved if you know who's moving. And the answer is, you know who's moving because somebody is going to accelerate to get up to speed, and somebody is going to have to turn around and come back. And somebody else won't feel any acceleration. So because we know the rocket must accelerate. And so when we get back to Earth, when we bring them back together, who's going to be younger? The twin on the rocket will be younger. Okay? So I'm going to finish for today, and I will be posting in about an hour some reflection questions for you to get the participation points. And it will be based on whatever I covered just now. So thank you guys very much. The key idea today was time is relative. I hope you have a wonderful day. Thank you for joining me. Wait. What time is this class over? Yeah, sorry, class is over. Darn it. I want to keep going, but class is over. Okay, and we will complete chapter 14 on Thursday. So have a wonderful day. I'll see you guys on Thursday. Okay, ciao. Bye. Goodbye. Where are you guys? Oh, I lost you. Bye. Mhm.